In this section of the course, we're going to learn about kind of what I think is one of the sort of the tougher problems in the beginning part of calculus, and that's the topic of related rates, okay? So in every calculus course, what you end up learning is how to take derivatives for a long time, and then eventually they pop this section on you called related rates, and it gives a lot of people problems, including me when I took calculus. Basically, it's a section of word problems, okay? They give you a bunch of word problems, so if you're not comfortable with word problems, initially you're going to be scared off by these, and then on top of that it's calculus, so you're not really quite sure what to do and all that stuff. But basically it's a section of word problems that involve rates, and we've already said a derivative is a slope or a rate of change of one function with respect to something else. And so what they do is they give you a lot of information, and from that you're supposed to solve for whatever it is they're asking you to solve for, and in the end you're going to end up having to take some derivatives in order to do that. We're going to work a few problems here. Don't feel like you don't understand any of this material if you don't just nail the related rates. You know, I'm going to explain these problems to you, and I'm sure that you'll understand how to do these problems, okay, because I'm explaining it to you. But in the end, when you get off and you go off and you work some problems yourself, you might feel like, man, I'm not getting this. Well, you just need to work problems. You got to work through them. Eventually, you'll start to see some similarities in what they're asking you to do. So let's go ahead and get started. What I'm going to do is I'm going to write a problem down over here, and we're going to talk about it for a minute and talk about a strategy, and then we're going to go ahead and we're going to try to solve it. Okay, so here's our first problem. We have a snowball, and our snowball is melting. And so as it melts, it gets smaller and smaller, and it tells us that the volume of the snowball goes down, decreases, at a rate of 1 cubic centimeter per minute. And it's asking us, what rate is the diameter decreasing when the diameter is equal to 10 centimeters? These kinds of problems typically just kill people because there are a lot of numbers in them and a lot of terminology. But a couple things you need to kind of focus on when you read these problems. The volume decreases at a rate of blah, blah, blah. At what rate, okay, is the diameter decreasing? My advice to you is when you read these problems, look for some keywords. One of the keywords is rate. Okay, when you see at what rate is something decreasing or something happens at a certain rate, what they're telling you in code is that, ding ding, the derivative, which is a rate, is such and such, or find the derivative at a certain point. Here, they're telling us the derivative of the volume with respect to time, the rate of change of the volume, is given by this here, and it's also asking us what is the derivative with respect to time of the diameter. In other words, how fast is the diameter changing with respect to time at exactly the point when the diameter is equal to 10. So you're going to have some sphere, which is a snowball, and it's got some distance, I don't know. At some point it's going to shrink. It's going to get smaller because it's melting. At some point, okay, the diameter is going to equal 10 centimeters. Actually, I've got this wrong. The diameter goes all the way through, like this. At some point, the diameter is going to equal 10. What it wants to know is, okay, as the snowball gets smaller and smaller and smaller, eventually it's going to get to 10 centimeters. At that point, when it gets to 10 centimeters, how fast is it shrinking? So they're asking you, how fast is it getting smaller when the diameter is equal to 10? So it's kind of a tricky thing, and this is exactly why, you know, these problems can be kind of difficult sometimes. But we're going to work it out, and we're going to work it out methodically. What we're going to do next is we're going to write down what we know, okay? We're going to write down what we know, okay? The volume of a sphere is something that you should remember. It's 4/3 pi r cubed. That should be something you just remember from geometry or something. But I know this. But notice that everything in here is in terms of the diameter, and this is in terms of the radius. So I'm going to rewrite this formula like this. It's going to be 4/3 pi, and I'm going to put the radius is just simply the diameter over 2 cubed. All I did was, this is radius, I changed it to diameter over 2 is equal to the radius. So these formulas are equivalent. I've just written it in terms of the diameter. So this will be, in the end, when you have a d cubed and you'll have a 2 cubed, and this will give you an 8, and 8 times 3 is 24. So what you'll have is 4/24 pi d cubed, And then when you simplify this further, what you'll have is pi d cubed over 6. So what we've done, the only thing we've done, is we've taken, we know this problem has something to do with the volume of a sphere, so I just wrote that down. But it also starts talking about the diameter, and I know that in the end I'm going to need to be talking about diameter and not radius. So I changed the problem so that what I have here is the volume in terms of the diameter, simplified it down. So really what you have is V is equal to pi d cubed over 6. That's the volume of a sphere in terms of the diameter. So this is one important piece of information. What else do we know? They tell us the volume decreases at a rate of 1 cubic centimeter per minute. So, like I said, that's a rate, which is code for a derivative. And the way you write this down is dv dt, the change in volume with respect to time, is equal to -1, which is 1 cubic centimeter per minute. The reason it's negative is because it's shrinking. It's getting smaller. The volume changes in a negative manner as you go in time. If the volume were getting bigger, it would be a positive 1. So you kind of have to read between the lines in these problems and figure out what sign the derivative actually is. So what are they asking us to find? They want us to find the derivative of the diameter with respect to time. What is that equal to when d is equal to 10? That's what this last sentence. At what rate, the derivative of the diameter, dd dt, what is that rate when the diameter is equal to 10? So I'm going to circle the relevant pieces of information here. Here's the volume of a sphere. Here is the rate of change of the volume. And here is what we're trying to find. This is what I recommend you write for every problem that you solve. Write down what you know, write down any derivatives that you have, and write down the derivative of what they're asking you to find. Okay? So, how do you think we should proceed? Well, here they've given us the derivative of the volume with respect to time, and here I have the formula for the volume. So let's go ahead and take the derivative of this formula. Okay? So, dv dt, which is the derivative of the volume with respect to time. Let's take the derivative of this guy, okay, which is going to be pi over 6 times, you got d cubed, so you have, whoops, I'm going to erase that. Then what you're going to have here is 3d squared, because you got the 3 that comes down, d squared, and I'm going to explain this in a minute to you, but it's going to be times d dt, okay? Now, what does this come from? What does this come from, you might be asking. We've never seen that before. Okay. Usually, when you have y is equal to x squared, and I say take dy with respect to x, what you have done is you've looked at this and you've said, okay, that's 2x. But always, just like the chain rule, what you've been doing all the time, but I've never really told you, is what you have over here is the derivative of the inside, which is x in this case. So what you've always been doing is dx with respect to x. This is kind of like a fraction, so it always disappears. You never see it, okay? In this case, you're taking a derivative with respect to time, okay? And so you're taking this derivative of d, but you don't know how d depends on time. So I guess the bottom line advice is when you're taking the derivative of something and the variable that you're taking it with respect to is the only thing over there, well then it's simple. You just sort of do it like we've always been doing it. But anytime you take a derivative of something and what you're taking it with respect to is not even over here. See, there's no time anywhere in here. There's no time here. There's just diameter. So you go ahead and you take the derivative like you would think you would, 3d squared, but then you've got to multiply by dd dt because then that fully expresses how everything changes. Here you're saying, you're kind of expressing with this term how d changes, okay? And here you're kind of expressing how d changes with respect to time. So that's really just using the chain rule. Here we're taking it with respect to time. There is no time, so go ahead and take the derivative like usual and then multiply by dd dt, and that will give you the final answer. And one more thing that I'll just sort of point out to you, what you're really doing here dv dt. When you do this operation, what's really happening is you're taking the derivative of volume with respect to diameter, okay? And then you're multiplying by the derivative of the diameter with respect to time. And these behave almost like fractions, so this cancels with that. And so in the end, what you arrive with is dv dt, which is what you're trying to find, you see. This is really a better way to explain it. When you do this 3D squared business, what you're taking is the derivative of the volume with respect to the diameter. But that's not what you're trying to find. So you've got to multiply by dd dt so that in the end you get the derivative of the volume with respect to the time. So either way helps you remember it. Go ahead and use that way. So let's proceed. We have this term right here. Now let's go ahead and simplify. So what's this going to equal to? Well, obviously that goes with that, and you're going to have a 2 left over. So you're going to have pi d squared over 2 times dd dt. You got to keep that because that's the truth, okay? But we know what dv dt is. It's equal to -1. So I'm going to switch colors here just to make things clear. So what you're going to do here is you're going to write pi d squared over 2 times dd dt equals -1. What you've done is you've calculated dv dt and you've arrived at this. Now you're just setting it equal to whatever they gave you in the problem. Okay? So let's solve for dd dt over here. The derivative of the diameter with respect to time is equal to, and we'll just move all this junk over there, so it'll be -2 over pi times d squared. You multiply by 2, you multiply or divide by pi d squared, so you arrive at this. Now look at what we have here, you see. What they're asking us to find is the derivative of the diameter with respect to time when the diameter is equal to 10. Now look what we have here. We found a formula that expresses the derivative of the diameter, the change of the diameter with respect to time, and it's in terms of d. So all we really need to do at this point is evaluate this, and this is what this vertical bar means, at d is equal to 10. This is the formula for the rate of change of the diameter shrinking as a function of the diameter itself. This is exactly what we need to find. So dd dt is equal to -2 over pi, and we're plugging 10 here, so we'll have 10 squared, so -2 over 100 pi, so -1 over 50 pi. So in the end, what you're going to have is the rate of change of the diameter, which is how fast it's shrinking, at 1 over 50 pi, and you got to have some units here, so that's going to be centimeters per second. That's how fast the diameter is shrinking when the diameter is equal to 10. So it's really a matter of having the problem down, figuring out what you need, and then kind of plotting a course. So my advice really, and you're only going to get this through working problems, is to write down the problem, draw a picture if you can, and write down any formula that's related to this stuff, and eventually you're going to end up having to take a derivative of the formula, and then you're going to have to eventually solve for a rate of some kind, and that'll be your answer. So let's try another problem. Okay, so here's our next problem. At noon, ship A is 100 kilometers west of ship B, and ship A also happens to be traveling south at 35 kilometers an hour. Ship B travels north at 25 kilometers an hour, and they're asking you at 4 p.m., which is only 4 hours later, how fast does the distance between them change? So this can be overwhelming if you're not really careful. And my advice, everybody, when I teach physics or any of these kind of word problems, you have to draw a picture. You really are not going to figure these problems out in your head. You're going to have to draw a picture. That's the only way it's going to become clear. So let's do this. I'm just going to draw a quick little coordinate axes there, like this. Okay. What we're going to have is, at the origin here, I'm going to put ship A. Okay? Now 100 kilometers away, I'm going to put ship B. It tells you ship A is 100 kilometers west of ship B, so as long as I make this 100 kilometers, this is okay so far. Okay? Ship A goes south, and I'm going to draw this in another color. The velocity here, I'm going to draw with a black arrow, goes south at 35 kilometers per hour, and ship B goes north at 25 kilometers per hour. Okay? And then it's simply asking me at 4 p.m., which is only 4 hours later, how fast does the distance between them change? So here you have a ship, and here you have a ship, and they're moving like this. So at 4 hours later, obviously the distance is a minimum here, and as the time goes on, the distance gets bigger, 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 bigger. Well, at 4 hours later, how fast is the distance between them changing? You should remember a formula called the distance formula, which is the square root of, just to refresh your memory, x2 minus x1 plus y2 minus y1 squared. So each term is squared. The difference in the x is squared. The difference in the y is squared. Add them up, take the square root. That's the distance. This is a distance. So if we plug in the values here, we could take the derivative of this distance with respect to time, and that's what they're asking us to find. How fast does the distance change? Derivative of the distance with respect to time. So that's what we want to find. So we want to find d, derivative of the distance with respect to time. That's what we want to find. So let's do that. But before we go in and actually do that, we want to go ahead and plug some numbers in here. x2 minus x1 is just the difference in x here. So this is just 100. 100 squared, okay, plus the difference in the y's. Well, here's where it becomes a little bit interesting. As time goes on, what we're going to have is the distance between them is going to be 25 times time, 25 kilometers an hour times time, minus, plus 35 times t. I'm going to explain this, so don't freak out on me here. And this is all raised to the 1/2 power, which is the square root. How do we get this stuff here? Well, at any given time, I want to find out how far apart are they. I want to find the distance in y. Well, this guy is traveling north at 25 kilometers per hour. So he's moving north, and at any given time, his distance, d, is equal to velocity times time. So 35 kilometers an hour times however many hours will give you how far away you are. And the same thing here, and he's going in the opposite direction. So I'm adding these up because the total distance between them and y is going to be the sum of however far they travel in that time. So you've got 100, which is a fixed constant in x. X is never changing, but y changes. The difference in y changes as a function of time. So to simplify this further, I've got 10,000 here, because 100 times 100 is 10,000. And then I've got plus 60t, and this is squared, and the whole thing is raised to the 1/2 power. Now I can simplify this further, and I can say I have 10,000 plus 3,600 t squared okay, and all this stuff is raised to the 1/2 power. Okay, so really all I did was I found out the difference in y, I added these two things together, still have the square out there, and then in the next step all I did was actually square this. So 60 times 60, 3,600, t squared comes along for the ride. Again, we've got the square root. Now I'm finally ready to take the derivative. dt, the derivative of this distance, how fast is this distance changing with respect to time, is equal to, got to take the derivative of this with respect to time. Again, I'm going to use that chain rule thing. So the 1/2 comes out, inside stays the same, 3,600 t squared. Exponent is negative 1/2, because 1/2 minus 1 is negative 1/2, but I'm not done. I've got to multiply by the derivative of the inside. The derivative of this is a constant, so it's 0. The derivative of this is 3,600 times 2t. Get this constant out front, the 2 comes out of the exponent, so it's times 2, and then the exponent of t is just that. Now luckily, because I don't want to do any more multiplication, this 1/2 cancels with this 2. They divide out, so I got a 1 there. And so, in the end, what you're going to have is dd with respect to time is going to be equal to, and I'm just going to basically rewrite this. What I'm going to have is 3,600 times t times 10,000 plus 3,600 t squared, all to the negative 1/2 power, like this. Okay. Now, what I want to do is I want to calculate how fast this distance is changing, but I want to do it at 4 hours later, because it says at noon these ships are here. 4 hours later, I want to know how fast is the distance changing. What we have found is a formula that expresses how fast this distance is changing. It's opening up. The derivative of the distance with respect to time is how much is that distance changing. And looky here, it's a function of time. It's a function of time. So I can put in 1 hour, 2 hours, 3 hours, and each number I put in here, it's going to predict how fast they're opening up. So what I want to do is I want to evaluate this at t is equal to 4, because that would be 4 hours later. So when you do that, when you plug in a 4 into here and a 4 into here, and so you have 4 times 4 is 16, and you have a 4 out here, and you multiply all this stuff, you take this negative, raise this to the negative 1/2 power, what you get is 55 kilometers per second. And I know I skipped a little bit of arithmetic there, but basically I put that in my calculator when I solved the problem, so you would end up doing the same thing. So you just put a 4 in here and you put a 3 there, if a 4 in there. If you put 10, like 10 hours later, what you're predicting at that point is how fast is the distance between those boats changing 10 hours later. So that would be at 10 p.m. So you've got to look at everything in the problem. Set your problem up, draw your picture, and figure out what the heck is it that you're trying to find, and then when you figure that out, write down any formula that you think you know that describes the problem. Go ahead and take the derivative of it if that's involved in what you need to find, and then kind of plug in what you know. And so we plugged in some of these values here that we knew. We took the derivative, and then we just looked at the time of interest, which was 4 p.m., which was just 4 hours later. You know, and they'll do that in those kinds of problems. They won't ask you 4 hours later, how fast is it changing? See, they'll make it 4 p.m. or something, so that maybe it won't be quite so obvious exactly what they're wanting you to do. Now here's a problem that's kind of interesting. You have a street lamp, a big light like on the side of the road, and it's 15 feet high. Then you have a 6-foot person some distance away from the base of the lamp, some distance RA, it's unknown, from the base of the lamp, and that person is walking away from the lamp at 5 feet per second. So he's walking away. How fast is his shadow growing? Okay, at that point. How fast is his shadow growing? So what you need to do is go ahead and draw yourself a picture. So here's a lamp. I'm going to put a little thing here like this. And this is 15 feet high. Over here, you got some guy, okay, and he is, I'm going to put it here, 6 feet high, right? And the light rays are coming out of this guy, hitting the top of his head, and it's creating a shadow this long. Because when you think about it, the light's coming down and it's projecting a shadow. Now, this guy is actually walking to the right at 5 feet per second. He's walking that way, okay? And the question is, how fast is his shadow growing? As he gets farther and farther and farther and farther away from him, like when he's over here, let's say, then you're going to cast a longer and longer shadow. When you're standing right underneath the light, you're going to have a real short shadow. So eventually, it's going to get bigger and bigger and bigger as he gets farther and farther away. My advice to you here is set up the problem like this. This distance, I'm going to call it RA. And to make this a little bit clearer, I'm going to take this right off of here, and I'm going to say this distance to the end of the shadow is RB. Okay? And I'm going to put a little arrow here and say he's moving at 5 feet per second, like this. So you have a 15-foot high pole, a 6-foot person, he's some distance RA away, and he's got a shadow that's RB long. And I don't know much here, and the question is, what do I need to find? Well, if this is the length of his shadow, and if they're asking me how fast is his shadow growing, what are we trying to find? We're trying to find DRB with respect to t. That's what we're trying to find. How fast is this distance changing with respect to time? That's what we need to find. So how do we go about doing that, do you think? What other information do we have? Well, if he's here, okay, this is the distance he is from the pole, and when he's moving at 5 feet per second, what does this mean? This means that the derivative of RA with respect to time is 5. I'm trying to show you how to put the information into calculus form, if you want to call it that. This is his distance. This is his position, okay? And he's walking, remember? This is his position. The derivative of position is velocity. I taught you that in the very first section. So the derivative of the position is the velocity, which is 5, and that's why he's walking along at 5 foot per second, okay? So here I've got dRA dt is equal to 5. I'm trying to solve for dRB dt. That's the answer to the problem, and I've got a couple numbers here, but how do I use them? If you remember back from geometry, you might remember something called similar triangles. Here's a triangle here, a big triangle, and here's a little triangle that's kind of tucked inside. These triangles are proportional to one another because they're the exact same shape, the same angle really is what governs it, but which is the angle down here, but they're just different sizes, so they're called similar triangles. So what you can do is you can write a ratio between them, and you can say this distance, 15, of the big triangle as compared with the distance of the big triangle down here, this leg, which is RA plus RB. So this, as compared to this distance here, is equal to this distance of the smaller triangle as compared to the smaller triangle's distance, RB. This is just simply a ratio because these triangles are similar. So the leg of the big triangle as compared with the big leg of the big triangle is the same as this leg of the small triangle as compared with this leg of the small triangle. Those ratios should be the same. So how do you go about doing this? You cross multiply to go ahead and get anywhere with this. So you'll have 15 RB is equal to, and this multiplied by this is 6RA plus 6RB. So you can collect your RB terms here. So what you'll have is 9RB is equal to 6RA. 15 minus 6 gives you 9, and you've got that over here. So what you have is RB is equal to 6 over 9RA. Okay, so then RB is simply equal to 2/3 RA. Now look here. What you have found is a formula that expresses this distance, RB, in terms of this distance. And the reason you're able to do that is because these two triangles are related to one another. If they weren't related to one another, you couldn't make any progress at all. So what we're trying to find is the derivative of RB, how this distance changes with respect to time. Look here, we have a formula for RB, so let's go ahead and do that. dRB with respect to time is 2/3, constant just stays out there, times dRA with respect to time. Okay? So the derivative of the left-hand side, the derivative of the right-hand side. So they're related like this. Okay? But look, we know what this is. dRA dt, it's equal to 5. So dRB with respect to time is equal to 2/3 times 5, because that gets plugged in there. And so you'll have 10 over 3. And that'll be feet per second, which is the same units as here. That's how fast a shadow grows. So you draw your picture. You've got to find something that relates the two quantities you're interested in. In this case, we had this formula that expresses how these triangles are related. We found a formula for RB in terms of RA, and then we took the derivative of both sides, and so you end up with this. And then you plug in what you know, which is given up here, and then you end up at RB dt. So really, I think you've probably realized, up until now, by doing these problems, that really the trick is figuring out what they're asking you and trying to find a formula that relates everything together. Once you find that formula, in one case it was the volume of a sphere, in another case it was a similar triangles, in another case it was something else. Once you find that, you can just take the derivative usually and go about your merry way.